and then I would like to hand over to Patrick Frey from BASF about material innovations.
Thank you. Thank you. Thank you. Hello, everybody. My name is Patrick from BASF. I would like to give you a short introduction, firstly about what is our department in BASF, what we are doing, especially with focus on e-engine. Afterwards, I will give some applications examples and also trends and requirements we see with a focus on electric systems, but also around thermal management and metal replacement, because we believe this might be also huge topics mid to long term. In BASF, we are splitted in different so-called core business and standalone business. And today I'm here with two of my colleagues, and we are part of the so-called materials division. And in this division, we are part of performance materials. Performance material means, in our cases, polyurethane foams, engineering plastics, which are typically processed via injection molding, like polyamide or PBT, but also thermoplastic polyurethanes. And additionally, we have also some, let me say, more advanced materials, a little bit special materials like PPAs and PCO. Additionally, beyond the material, we offer a wide range of services, like also kind of in-house consulting and in-house simulation service, as well as technology development. I will also show later a few real-life examples to get a better idea what's behind that. If we talk about plastics in general, first of all, it's important to mention we are not active in these, let me say, wide mass market of polypropylene or and so on. So we have typically, you see here, these plastic pyramide with the x-axis amorphous and semicrystalline polymers, on the y-axis typical material requirements. And as I said, we have typically a wide volume use of standard plastics, and here we are not active. We are active in the field of so-called engineering plastics and also in some high-performance plastics, which are mainly used for technical applications. And today, I would like to show you some examples around the e-engine. So we have also a small booth here. As I mentioned, we are 3 colleagues here from BASF today. And we have also this example here with us today at the booth. So we will also be here today and tomorrow. So also if you have a question afterwards, feel free just to have a look at our booth and have a short discussion. I will start today with some examples around high voltage power electronics. Then coming also to the e-motor and the cooling system, as well as the coolant system. And as I already mentioned, also some examples regarding lightweight and NVH solution. If we look on electrical applications, what we see typically as a huge trend are materials which withstand the so-called UL94 test. So it's a burning test, more or less. You have a test specimen, you burn that specimen, and you want to see the behavior. Does it still burn or not? And at UL, you have different classes, so-called HB, horizontal burning, V0, V1, and V2 classification. And at the end of the day, they all give you different results based on your plastics. What's here important to mention, I mean, we see these tests as a quite common requirement in the E&E industry. But what we do here is we do the test completely in-house. So we have a certified laboratory in Ludwigshafen in BASF. So we produce the test specimens, directly run the tests in-house, and they are, as I said, certified. So we see a huge demand for these tests, but we are able to cover that also, I would say, with a high speed. Additionally, we see much more demand also for so-called RTI listings. So in this case, especially if you talk about power electronics, it's a value what is often required, the so-called relative temperature index. It's a value which describes mainly the material performance after aging with temperature. And here you have on the yellow card, it's a typical yellow card provided by UL. You have these different listings for RTI electric, so the RTI strength and also the impact strength. And what we see as a trend is that especially RTI electric values are much more requested at the moment compared to a few years ago. power electronics, and also the values are getting higher. So the required values, in past we talked about 140 degree, typically what a material need to withstand. Now we see more 150, 160 degree, up to, in some special cases also 180 degree. Another application which is also quite close to the power electronics, but maybe with a complete different requirement are the so-called high voltage connectors or plugs, what you see here. And here, I mean, we have also all these electrical requirements, but additionally, you know, it's most of the cases these are orange colored. And RAL 2003 is I would say the most common color which is used for electrical vehicles. But here we have some issues, especially if we talk about RAL 2003 with polyamides. You see here a typical aging behavior. If you take a PA66 with 30% glass fiber reinforcement, 1,000 hours, and age it, for example, with 90 degree, you see uncolored product still keeps uncolored. If you increase the temperature, you have this kind of brown effect, so it's getting brown over aging time. And this is something you don't want to have with your high voltage connectors, because in case of an accident, I mean, you sure want to see that is high voltage in the car and not any low voltage grid. And then we said, okay, let's just color it, and maybe the effect is gone, but unfortunately this was not the case. So also if you see here, if you take an orange pre-colored material and age it with temperature, it still will be brown after time. So what we did, we started the development to decrease this effect as good as possible, and the result is shown here on the right side. So you still see a kind of effect, so it's getting a little bit into brown, but will still be orange after aging, to make sure that you could identify your application also, as I said, in case of an accident. So you see very, very close together in the e-engine, two applications with completely different requirements. The third example I have here regarding electrical applications are the sorry, I missed one important test, the CTI test. I already had today a nice discussion with one of the colleagues here. So CTI test is typically a test which simulates a kind of tracking by a wet surface. So you have typically here these two electrodes. You have a kind of dripping liquid, and you test several voltages. And at the end of the day, you don't want to have a sample looking like this here. So you want to make sure that there is no real kind of arc applying what you see here. It's especially relevant for, like I mentioned here, for connectors or high voltage components. But it's important to know that the practical test has nothing to do with the norm, how you use these tests later on in the real part. Because what you typically measure here is typically, according to the norm, you measure a value up to 600, so typically called CTI 600. But it doesn't mean that you could use just this material for applications with maximum 600 volt. This is something what sometimes is a little bit misunderstood in the industry. So you see here also some example. Typically it's combined with having a material insulation glass, having also a kind of contamination glass of your application. So in case of it's sealed or not sealed, you have different glasses. But you see here in this table, you are also allowed to use a CTI 600 or 400 material in an application with 1000 volt, but you just need to increase the thickness, the distance of your metal pins. So but it's important to mention, it's really, you could use also CTI 600 materials for 1000 or 1500 voltage applications. This is, I would say, in the uni industry also commonly in use. So there's nothing untypical here. The third example I have here for you is regarding bus bars. So they play an important role if we talk about the e-engine. Here we have also another test additionally coming, so-called thermocycling test. So you see here, typically you have a kind of expansion behavior from your metal and your plastic. And if you increase and decrease the temperature, at the end of the day, you still want to have a working application. And you want to avoid something like that here, like having these cracks here on the surfaces, which might cause a failure at the application. What we made here also is we deeply involved our simulation department, and we developed an own material model where you could simulate at the beginning the typical flow behavior of the injection molding process, take the fiber orientation out of that, and based on these two information and much more measurements we did, making a kind of thermal stress analysis and seeing, okay, where might be an area which is critical, or where is it uncritical in terms of thermoshock performance. If we come to especially contact with oil, we also made several tests. So together with a big European OEM and company Shell, we also made several tests and also investigations. We tested 9 so-called EPs, so engineering plastics from our side, in combination with a new kind of oil version, 2 temperatures. And what you want to see here is, at the end of the day, does the oil have an impact on the EP behavior? And otherwise, also, does the EP have an impact? Is there maybe something coming out, have an impact to the oil? At the end of the day, I could say we made this big study and there was no real surprise. So it was the results were all in the expected range. But still important to know, if we talk about also combination of coolants, that you have a kind of influence. So especially with polyamide, PS6 and 6.6, there is an influence. For example, here you see also overaging. For example, here 3,000 hours, stress at break. So you see a slight decrease. So there is an influence which is important to mention, especially during the design of the part. So it's not like taking a tensile strength out of the data sheet. So if you have this kind of contact with, for example, here LECC, also same for the strain at break, you will have an influence on your final part, and you need to consider that during the design of your application. We also tested these for the change of the conductivity here in this case, and there also a typical target is also to be lower than 300 microsiemens. Also here we are in a good range with our materials. Same is also for the pH values. Higher than 7 is typically a requirement, and also here we've seen no issues with the latest developments. The next topic is more about, as I mentioned, metal replacement. So I would say we have a strong background in so-called engine mounts for typical internal combustion engine, so the fixation from the engine to the chassis. This was in past quite often done out of here aluminium die cast or stamped steel. And we developed together with our partners for sure some solution out of PS66 or PS6. Main target is for sure weight reduction, so up to 30 to 50%, depending on the design, the initial design. Also better NVH behavior, as well as, I would say at the moment the most important point, the cost reduction. So also up to 15% cost reduction. But here's also the story. I mean, how does it work? It's not like having one geometry and take it and make it out of plastics. So it's important to say we start typically with a geometry. If you already have a good plastic design, we could directly step in the filling analysis. It's also the whole workflow here could be done in-house in BASF. So there's some kind of offer we have. We typically check the fiber orientation because for fiber reinforced plastics it's important to know this. And then we also make the kind of static analysis, also crash analysis. And if this is everything okay, then typically a customer of us says, okay, let's go in a prototype tool. Because I mean, we also learned today, in some cases prototypes are cheap. I would say in injection molding they are quite expensive, so you try to develop as much as possible virtually. But sometimes we also have the case that we do not have let me say, the optimum shape. I mean, because here you see, for example, you see here the ribs are completely different in the plastic part compared to the metal part. Also here you have, I mean, it's full material. Here you have just this rib structure. If this is the case, we also support with different kind of optimization methods. Here in this case called topology optimization. So it's typically you have a kind of a shape of an application. You have a kind of so-called design space, and then you act the force and fix it anywhere. And then this optimization tool shows you where do you need material or where could you remove material without having a significant influence. And this is what we do, I would say, really since a long time. So taking also optimization tools and methods into account. Here you see, for example, a lower bumper stiffener in a car. So this was the result also of the optimization. And then typically the designers try to put these result in a real CAD shape geometry. And I mean, also here, ideas could be possible. We see also some potential if we talk about transmission cover in an e-engine. I mean, we have it also here at our booth. So yeah, I think we also need to think a little bit more open for future, because there might be some huge potential also here possible with engineering plastics. The last example I have here today is regarding a plastic metal hybrid concept. I mean, we still talk about in case of covers. I mean, the flat cover maybe not so, but in complex cover structures, we still talk about, okay, could we replace it anyhow with a Verbund structure? And in this case, we also made some test parts. So it's a kind of metal sheet with thin plastic layer, and with these parts or this setup, you are also able to overmold it with ribs. For example, here you see ribs and also fixations and so on. And yeah, we believe also that there is weight reduction up to 20% possible, depending on the geometry. We also see some huge effects on cost reduction. So yeah, we also started now these activities because we see some potentials for future in replacing a full metal part with a plastic metal hybrid part, to be still in scope and reduce the costs. So finally, I mean, we have these called application-oriented solutions. So yeah, we try to understand the requirements of our customers together with them, try to support as good as possible. It's, I would say, in most of the cases really customized, so it's not like one plastic fits all and also one technology fits all, so really depending on the application. We have already in past a lot of successful projects realized. Many of them are also published, so if you look for a BASF and write ultramid and, for example, engine mount, you also find it public. So yeah, we have a lot of success stories realized with a lot of technical expertise, I would say. I think this is still a big point for us. So we have these lot of technical experts which support you during development. And and for sure beyond that, I mean, it was not part of the main presentation today. For sure, we also offer most of these materials also in a kind of sustainable version. So beyond that, I mean, it was not a topic of today, but it's important to mention we have also clear CO2 targets becoming greener in future. So we have also for most of the products a kind of sustainable version available already now. So okay, that's my side. So thanks for having me here. And
so thank you, Patrick. And as said, the last round of questions. Last time I thought nobody will ask, and then they never stopped asking.
no, I mean, as I said, we will be here today and also tomorrow. So yeah, if you have any question, feel free to come to our booth.
It's also, I would like to invite to talk to all other presenters. I guess we have enough input for questions for the lunch break in the whole day. So thanks for all who contributed this morning. And then we have lunch break until 2 p.m. And yeah, happy for discussions.